So hello everyone. So it's great honor for me to introduce my research result in front of real people who involved in combat education activities. So I'll introduce my recent result for monitoring of sandstorm generation and modeling using satellite image and UAV. Okay. Okay. Yeah. Okay. So first of all, let me introduce what we aimed. So we aimed comprehensive mapping of ongoing desertification, and consequent of the storm generation pattern for full Mongolian territory case. Okay, technical basis of this work: intensive remote sensing data collection, especially focusing on aerodynamic surface property and aerodynamic erosion. Especially, we integrated UAV drone data together with the satellite, so we can take the precision of UAV and extension of satellite data together. Okay. Okay. Thanks, sir. So instead of one-time observation of sandstorm monitoring, we take long-time time series analysis, try to find out the change of desertification source. In final stage, modeling and monitoring system will be integrated. So this is proposed mapping and modeling system. We integrated all kind of data set, including the climate factor and the radar satellite, especially, and drone data, and some of physical modeling to extract some kind of surface characteristic. The simplified model is quite straightforward. We want to extract somehow relationship between surface property and the migration of surface through UAV and drone observation. The different things, general research approach. First of all, we constructed some kind of prototype processing model. We implemented this one to regional institute, not for only our own study, for future application in regional institute for their own sandstorm monitoring work. Okay, so once we establish the system, we go to Mongolian Institute of Remote Sensing. We make almost 35 hours of intensive training about data processing throughout this syllabus. And then all personnel of Mongolian Institute people had some kind of manpower for full data processing. And then we hope in future they also can construct their own sandstorm mapping system. This is quite different approach. We do not want one-time research. We want permanently available system in regional institute. So let me show the outcome of data processing. First, satellite data. We construct all of our system based on some public domain software, so-called Google Earth Engine, which has provided publicly available in API. So in any time, so we can construct a spatial domain which is covering all of target area, Mongolian area, for last 20 years with just 1 hour's time investment. We construct almost 60 different the spatial data set with only 2 hours time investment using our constructing system. So first of all, we investigate the effectiveness vegetation index, which is usually employed for sandstorm monitoring system. So here we find the weakness of vegetation indexes. NDVI, LAI, which is commonly used for sandstorm, has so much problem because of saturation issue. EVI also has problem because some of vegetation biomass which has no photosynthesis but it is very effective to prevent sand dust storm. Does not catch it by EVI. So we abandon vegetation canopy to employ for employment of sand dust storm mapping. Okay. Instead, what we employed protrusion coefficient that represent surface local roughness. Because rough surface can effectively prevent sand dust storm generation. So that's why we implemented the protrusion coefficient, so-called protrusion coefficient, which is extracted modest satellite data analysis. We applied protrusion coefficient mapping in China Kubuchi Desert. Very effectively, we discriminate all of sand dust storm mapping area, sand storm source area from vegetated area or combat desertification area. Even we can effectively trace the establishment of barrier for sandstorm generation throughout combat desertification. Okay, so I want introduce a detailed part of physical modeling because mathematically is very complicated, but I'm sure that's the most effective way to map sandstorm source area. So in Mongolian case, I brought that system for full extent of Mongolian sandstorm mapping covering almost 20 years of time. As I told that, we just need to invest 1 hour of time to extract all data set covering whole Mongolia with 500 meta resolution. Then what I did, we apply some kind of time series analysis, which called empirical orthogonal function analysis. Through that empirical orthogonal function analysis, what we can see for last 20 years, constant sandstorm generation area first. Then in second component, we see expanding desertification in northern area, northern Mongolian part. So this is certain kind of dynamic mapping, not static mapping. Then we have to validate satellite data throughout ground survey. So this is the pathway we follow for almost the last 1 year. We conducted 10,000 kilometers of the ground survey together with the drone and 4 people and 2 cars. And first times before sandstorm generation season and then after sandstorm generation season. We just follow up the major part of southern the Gobi Desert and then the summer season we also repeat same pathway but including the Kowloon River which propose the major expanding area of desertification. Okay? So like this way. In each area we make 2 or 3 times the UAV drone observation, we constructed a high-resolution stereo model to extract the physical characteristic of sandstorm source area. So this is severe environment of Mongolian sandstorm source. You see the winter time, many dangerous situation. Here is one photo. If you have any background in geology or geomorphology, you can find out many clues. What is the main sequence of sandstorm generation in Mongolia? What is the most effective way to prevent sandstorm generation? Okay, so this is the last my drone. Looks like I'm very happy because even minus 20 degree, I accomplished very nice drone work. So basic theory of this one. We can calibrate protrusion coefficient, satellite-based protrusion coefficient throughout drone observation. Mathematically, we can only remain above surface structure throughout some mathematical machine vision algorithm. Then we can calibrate the PC2ZO, that called aerodynamic local roughness length. That is the most important parameter for sand dust storm generation. Now let me show one example case. This is a planting area by Ministry of Forest Korea in Mongolia. We constructed the stereo modeling, and then we also constructed the bare earth stereo model. Then subtract these two, we only can remain ZO parameter. That is the element which prevent dust storm generation. So we can calculate ZO parameter. So that case, the other, around the Kowloon River, you can see very, very horrible things in here. The area looks like grinded by sandpaper because millions of wild rats eat up all of vegetation biomass. For all of my life, I never seen such kind of horrible thing. For almost 6 kilometer radius, I can see any living thing. So in that area, ZO parameter is almost equal to 0. So it's very fragile to sandstorm generation. This is undergoing desertification around the Kowloon River because diminishing of river channel, desertification is expanding, ZO value is decreasing. That represents the natural vegetation, how effectively prevent sandstorm generation. Compared with artificial forest, by combat desertification, 30 times more effective. It is 30 times more effective. Then so we can calculate the relationship between ZO and PC parameter. Of sand dune area, you can see there is no ZO parameter. Okay? If we effectively apply all of machine vision algorithm, we only can remain only ZO parameter element. It's a difficult task, but almost 24 sites, we effectively calculate the ZO parameter. We also precisely calculate ZO to PC to ZO calculation, like that, like that. There is some regression. On the other hand, I also noticed there is some undergoing artificial effect in sandstorm generation in Mongolia through mining activity. So world biggest surface the coal mine in here. In every year, I estimate almost 30 million tons of mining dust in mixed up dust storm, like here. As you see in satellite image, you can see the progress of the mining activity through south. Radar satellite observation, you can see the large amount of deformation, which probably mixed up the dust storm, sand dust storm. Now we go to model and monitoring system, how we can use all of this information. We need to introduce certain kind of observation, where is the sandstorm area. So we introduce radar satellite phase coherence, so-called radar satellite phase coherence. This is very effective where is surface erosion. This is the application of Kubji data. You can see where is eroded area, where is very well preserved area.
Professor, excuse me, Professor. At 1 o'clock, Mr. Ibrahim will be here, so we have to conclude the session.
Okay, so I shortly
please do.
Yeah, I shortly complete this one. We constructed another algorithm, and then what we finally managed, the monitoring system combining UAV and radar satellite images through many difficult mathematical modeling methods. And then final stage, we now find out millimeter level, vertically millimeter precision of surface erosion map, as you see here. Okay, this is final product, and then from surface characteristic, we also constructed the modeled erosion map. Let's go to the full Mongolian area, combining ECMWF weather model and surface characteristic. Now we can define surface the generation eroded map, which is corresponding the sandstorm source area. Okay, this is the final product. So you can establish pool area, any pool area sandstorm generation map with just 1 hour's rover. Okay.
Thank you, Professor. The now last speaker of the session is Professor Lee.
Namaste. According to the time schedule, there's a little time left for me. So I will try my best to finish. Before the presentation, I will give a brief introduction. I come from the Chinese Academy of Sciences in the Aerospace Information Research Institute. My topic is I will to give a case study how to improve the soil properties mapping with high spatial resolution and high accuracy. I think it's very important to the sand dust storm, the mapping, because soil properties is the most difficult to acquire at the large scale, especially based on the remote sensing. Okay, next. My presentation including the 3 parts. Firstly, I will give a brief introduction of the background. Everyone knows the desertified land is the major sandstorm and dust sources. So it's very important to master the soil properties of these regions. It's very important. We can see this is the sandy lands in the northern China. Also, the soil organic matter is a key factors to determining the formulation of the particles in the sandstorms or the dust. Also, it's an important indicator of the SDG 15.3 progress tracking. So, however, acquiring the soil organic matter below ground still face many challenges at the large scale. And the Earth observation technique with the ability of the real-time, repeated, and large-scale the data query ability, which could provide the valuable opportunities for the SOM mapping at the large scale. That's what we to do in China. This slide, I will introduce existing products and their limitations of the SOM. We can see this is the SOM map of the China. It's from the Nation Soil Survey of the China. Its visual spatial resolution at 2 kilometers and the time is 1980s. The measures is mainly based on the interpolation based on soil profile as the nation scale. This is the national data set. Also, we can see the international data sets about soil grids, 250. The spatial resolution is 250 meters. The time is not clear because all the samples is from the different countries. The time of collection is not sure. It's a span from a very long period. The measures is based on the machine learning based on the model set and the other ancillary data sets and the soil profiles globally. I want to note for the China, the soil profile is the same. This one is the global soil organic carbon map. It's just released in this year. And the source is from FAO. And the spatial resolution is 30 arcsand, approximately at several hundred meters. And the time is variable according to the soil samples. The measures is multiple measures based on the nation data sets. It includes the linear regression, the machine learning methods, and the other methods. So what's the limitation for the sandstorm and the dust soil conditions mapping? I want to see for the North China, we can see the soil sample is the same. All the soil sample is mainly for the cropland, for the agriculture, not for the natural drylands, not for the high-risk soil, sandstorm and dust areas. The second one is the spatial resolution is lower. All the products, the resolution is lower than 250 meters. it can't reflect the heterogeneous landscape in the drylands, especially in the drylands. The third limitation is the time. The product, the time is outdated, it's static, it's updated very slowly. So what we want to do is to give a high resolution SOM mapping, and which can't be updated very quickly based on the Earth observation data. That's what we would do. The second one is the major achievements. This is the study area. We can say it's the whole northern China. The brown points is the soil sample points. It covers the major sandy lands in the northern China and the different degrees of the desertification areas. For the satellite data, we use the Sentinel-2 data. It's provided by the ESA. We use the data provided at the Google Earth engine. Totally, we use the data from the 2015 to 2018. The time is the non-growth season to reduce the effects of the vegetation signal on the soil information retrieval. The process includes the cloud mask, the NVMX composition. Then we get the data of the Sentinel-2 data of the whole regions. All the work is completed at the Google Earth Engine platform. This is the soil samples. We analyze the samples collected from the field in the laboratory, then get the data. We can see among the 243 samples, approximately 43% of the samples have a SOM content lower than 0.2%, while only 4.5% of the samples are higher than 2%. This reflects the whole regions is with the lower SOM content. The model inputs and the scenarios, the roles of the Sentinel-2 and the other data were studied through running each model with different specified inputs. The first one, we just consider the characteristic factor. It's used like the traditional digital soil mapping. We don't use the remote sensing data. The second one is we consider only the remote sensing data. And the third one is we use all the informations, but only the factor significantly correlates with the SOM was used in the models. This is the different the factors of the model inputs. This is temperature, it's precipitation. This is the variables optimization. It reflects the correlation between the different factors with the SOM. Finally, we use the band reflected, the two vegetation indices, and the climate data like the temperature and the rainfall. Also, the soil surface moisture is included in the models, and the elevation, the topographic, the factors is include models too. For the models, we use three models. The first one is the multiple linear regression. It's most widely used models. It's simple and convenient. The second one is the machine learning models. The first one is the classification and the regression tree. And the second one is the support vector machine. I don't want to introduce the two details about the measures since we have limited time. For the models running, we firstly solve the question of the parameters optimization for the machine learning measures, since which is very important for the success of the models. Also for the model validation, 20% of samples was removed in advance as the independent validation samples is used for the validation. This is the model performance, the result between the different models, different inputs. So we can see for the different models, the overall performance of the cut is better than the SVM model and the MLR model, which shows the machine learning measures could improve the SOM content prediction accuracy. For the different combinations of input variables, the best accuracy is gained when all variables significantly related with SOM content were utilized. This is the SOM distribution map of the whole study areas. Also, we compare our products with the international existing products, such as the World Soil Database and the Soil Grid 250. We can see the Soil Grid 250 overestimates the SOC in the delta flight in the northern China, according to our samples collected on the field. The second one is we can say the estimates the SOM could reflect the series, the degree, the series of the land dedication. This is map slide shows the advantage of